Here, we're going to be talking about doing the t-test directly. So instead of the previous, more broken down approach that we followed by calculating the standard error and the t-score and then inputting that into the probability function, we can actually calculate the t-test directly in R, which gives us all the results that we need. And you need to do that, you need to have two separate samples or just two variables in the single data frame, and both options actually work for this t-test function. So let's take a look at both of them. So option number one is, so the both, once again, they're both the same functions, just different ways to set them up, and both of them works. So the function is t-test, open parentheses, close parentheses here at the end. And we have uh, with two variables, but notice that this is one data frame that we created for the mothers and newborns data set. So one of smokers and one of non-smokers, and sometimes they're called X and Y, but this does not mean that this one is the causal variable and this is the outcome variable. They're just two different variables. But notice that we are using the weight variable from the smokers data set, and then also the weight variable from non-smokers data set. And we created these from the subset of the same whole data set here. And this is the weight variable. And we use that habit variable to separate these two here, smokers and non-smokers. And we also have a last parameter here regarding variance. So this var here is referring to variance. And we're assuming that the variance among these two variables is equal. And this is not always the case, and sometimes the variance is not equal, in which case we should put false here, but we'll examine this shortly. The second option is, once again, the same t-test, but we just set it up a little bit differently, and we can use the same one data frame, so we don't need to break the data frame up. And we can only do that if, well, we have the one variable, the quantitative variable. We're talking about quantitative inference. So this is the weight variable. So that's the main variable, the average of which we're measuring. And then this is the grouping variable. And habit, in this case, is habit here from the data set. And it only works because we only have two possible values, smoker and non-smoker. It could be 1 or 0 or yes or no, but it has to be only two values for this grouping variable here. So the first one, this is the main variable that we're measuring, and then the tilde, and then the grouping variable, and then comma. So that's the second parameter. This is the first set of parameters. The second parameters, data is the name. Always going to be data here, but then, of course, whatever data frame you have, you put it on the right side of the equal sign. That's the data frame that we're feeding into the data. And then also the variance parameter as well. We're assuming it's true, but we also need to check that assumption. We'll talk about that. So this is how we do the t-test directly. Now, what I'm actually going to do is walk through doing this t-test directly with the COPD data set that we used for our previous lab, because we already have that data set, and then we can walk through the calculations, and it should be understandable to you. So we're going to test whether or not the MWT1 best variable, which is a walking distance measure, it's a quantitative variable, is different between female and male COPD patients. So actually, if we were to set up here the null hypothesis, is that the mu of males minus mu means the population average of females, and mu in this case, once again, referring to walking distance, equals to 0. And the alternative hypothesis that the mu of men, the difference between the mu, I'm sorry, this looks like an M, but it's supposed to be a mu. Oh my, let's address that real quick. Mu for females is different than 0. So different, so there's two tests. We don't know if it could be less, it could be more. So we're doing a two-sided test here for the difference between the two. MWT1 best is the quantitative variable we're comparing, and we are comparing it between genders. This function only works as such because there are only two levels of gender. So if there were more, it wouldn't really work. but we could break the data down to just two levels. That's what we would have to do. But we were doing that second option here. So we're using that one data set. So this is the COPD data set. This is the data frame, the data set, the main variable that we're measuring on the left side, tilde, the grouping variable on the right side. And then we are assuming equal variance. And this is the result of the test over here. So I did run that and we got a result and we got everything that we need here. P-value, degrees of freedom, the alternative hypothesis stated. Once the alternative hypothesis, that true difference in means is not equal to zero. So that's the way we set it up here. There's a 95% confidence interval. Now, is this confidence interval that must be for both genders? It's kind of hard to tell. But the sample estimate is separated. So mean in group 0. So that's man, and then mean in group 1, which is female. So we can see that on average, the walking distance for female is greater than for male. But once again, as we've been talking about in this class, this is not sufficient. We want to know about not just that one measure, but we want to know how it behaves across the distribution. So we do the hypothesis test, and the p-value is 0.1705, which is very high. It's greater than 0.05, and it's certainly greater than 0.01. So that means that we cannot reject the null hypothesis. We cannot reject the null hypothesis, and we cannot accept the alternative that there is a true difference in means that is not equal to zero. So we remain with this idea that we do not have statistical evidence that walking distance in COPD patients, because that's the data set, is different across these two groups. It's not different enough. Now, I'm going to introduce some new concepts here we haven't talked about, and I'm just going to focus mostly not on the theory, but just how it is applied. And that should be easier, and hopefully it will still make sense to you. So there's two assumptions that we're going to test here with an actual function from R. So first is the normal distribution. Now, we already examined, from the new mothers, newborns and mothers data set, whether or not it kind of looked normal with a histogram. And I think we may have done a little bit of this with this variable as well, this walking distance variable in this data set. But we can actually compute it more precisely with the Shapiro Wilk test. And the Shapiro Wilk test assumes the not whole, but null, the null hypothesis assumes normality. So then the null hypothesis that it's normal. So we want to have a really low p-value to be able to reject that it's not normal, to reject the idea that it is normal. So here, this may look a little bit strange, but because we're using this with function of R, which actually enables us to put everything together and facilitate the calculation. So we're saying with the COPD data set, the data frame, comma, so that's the first parameter. The second parameter is a function. So we have a function inside of a function. And here, the second parameter is the function itself, the Shapiro.test function. And in it, we identified the main variable of interest, WT1 best, and then the grouping. So we're working just with that whole data set. We didn't break up the COPD data set into two. And then so where the gender equals 0, so that's for, remember that double equal, this is when we're comparing. So here's the comparison. This is kind of like a filtering or a condition testing. So where gender equals 0, calculate this normality in this data set. That's what's going on here. And then the p-value is 0.5071. 0.5071. So that's a very high p-value, and it's much greater than 0.05. So we failed to reject the assumption of normality. So this is normal. We can we find it as normal check. Now, for the other gender, female gender, for women's walking distance, we do the same thing, but the result is much lower. And this is less than if we have the 0.05, or even if we had 0.01 confidence level, it's still below that. In other words, we reject the null that it's normal, and this looks like it's not normal. So for the female data set, it's not normal. So even though it may have looked like it was normal before, but when we do the test, it's not normal. So we do not have a normal distribution for part of this data. Now I'm going to show you what to do in this case. If the data are not normally distributed, it's recommended to use the non-parametric two samples Wilcoxon rank test. So if the data is not normal, if only just one of them not normal, we use a different t-test. It's called the Wilcox t-test, and it's very simple the way it's applied. So it doesn't really change much, but just remember, if the data is not normal, we use the Wilcox test instead of the regular t-test, and I'll show how that goes. Now the second test is so this was the first. We're just doing two. We're testing normality, and then we're testing equivariance. And we do to do a test of equivariance, we use this F test, the Fisher test, where the null hypothesis assumes equivariance. And to do that, it's called the variance test, var.test. So you input this into R. We have the main variable we're testing, and then we have the grouping variable, and then the data frame that we're getting this data from. So this is the variable, the grouping variable, and then the data frame. And then once again, it gives you the results. This is all the results from R. And we're most really concerned here with the p-value. So this p-value is very high. So we do not reject the assumption of equivariance. So equivariance it remains, the null hypothesis remains equivariance. So regular t-tests assume equivariance. If somehow our two vectors, meaning two variables, do not have equivariance, we should indicate this in the t-test parameter. The t-test will then run a Welch t-test, it's called, and then we just change that last equivariance parameter to say false instead of true. Now here, for this data, we did not reject the idea of equivariance. We keep equivariance. So we would not put false here when we do the t-test, we would keep it true. But if this p-value was too low, below 0.05 or below 0.01, then we would change this parameter to false. So only if p-value is less than 0.05 or 0.01, depending on how strong or how confident you want to be. And so the final t-test, considering assumption tests. So in the COPD example, since the M1T best for women was not normal, it was equivariance, but not normal, we will use the Wilcox test. I noticed that in this, when we apply the Wilcox test, there is this extra parameter here that we didn't talk about, this exact parameter, and that has to do with using an integer rather than continuous variable. So this measure of walking distance variable is actually integer and not continuous, like a decimal. So sometimes that will give problems with the Cox test. So just make sure if you do have that kind of variable in the, you use false for the exact parameter. But everything else looks the same as the t-test. So it's just called Wilcox.test. The first variable is the main variable we're testing. The second one is the grouping variable separated by tilde. Then we have the data parameter, and the data frame is COPD, and that exact parameter I was just talking about. And this is the result over here. Wilcoxon rank sum test with continuity correction. And the p-value is 0.2911. So we we failed to reject the null hypothesis here too, because it's very high. And if we take a log, I copied also the results from the previous t-test, where when we use the t-test instead of Wilcox test, because we assume normality, and we also can keep the variance equals true as we had before, because we did the Fisher test for that, of equivariance, the F test. It showed that we should assume equivariance. And then in this two-sample t-test that we had originally done, the p-value was 0.17. So it is also failed to reject the null of differences of gender in the COPD data set regarding walking distance. So they both failed to reject, but this one is even more kind of reject, even worse than this one in terms of the p-value being higher. But they both led to reject the null hypothesis. I'm sorry, failed to reject the null hypothesis that there is a difference between genders in walking distance in COPD patients. So here, just a last summary of the procedures. Hopefully this kind of wraps everything up together. First idea is, are we comparing two separate unpaired means of an independent sample? So that's the basic idea we have to understand first to know if we're actually going to follow these approaches. Then we want to set up the null and alternative hypothesis. And usually you want to just set it up as equals the difference between the pairs are equals 0 or different than 0, but you can also do a one-side test, equals 0 or different than 0. But we can also do maybe equals 0 or greater than 0. This is easier to make it easier to reject the null hypothesis. It's harder to do a two-test because you have to reject on both sides. But if you just look at one side, if you do a one-sided test, you can also do that, and that's easier to reject the null hypothesis with a one-sided test. Identify your confidence level. Do we want to stick to 0.05, or do you want to be more conservative and stick to 0.01 as the threshold at which we would reject the null? Then we test for normality assumptions with Shapiro Wilk test, which we introduced here. It should be pretty straightforward to test for normality. And equal variance assumption with the F test. So these two tests here, we introduced. If normal and equal variance, use R as the t-test function, and then make sure equal variance equals true. If normal and unequal variance, use R as t-test function, but with the correct parameter changed, equal variance equals false. And if not normal, then use the Wilcoxon test function in R, which follows the same standard as the t-test. And that kind of wraps it up for us. I hope this was useful to you, and I will see you next time.